Thank you, Matt, for the kind introduction. So I'm presenting this paper on behalf of my co-authors and especially Bing, who, for obvious reasons, was not able to attend. But she was very kind to prepare the slides, and it's time for us to experience them together for the first time. I have the timer on. Okay, cool. So let's start with some context. Right. So these are some cuts from Bing's favorite movies from Bing's favorite directors, the Coen brothers. And so as we see here, oftentimes in a long shot, only a small portion of the scene is changing, be that a person or a car. And this is a common scenario also in interactive applications where only a small portion of the scene is moving or being edited at a time. And naturally, we want to take advantage of this temporal coherence to avoid redundant computations when rendering those frames. So here's our problem setup. We have this initial rendered frame, and this is our new frame. Here the chair has moved to the left. Now, instead of rendering this new frame from scratch, we want to render only the difference between the two frames. Why? Well, here we see that this difference image generally has lower energy, and if we do things right, we can hope that we can render this difference radiance with less variance. So yeah, then we need to figure out which light transport paths actually contribute to this image and focus on them. Here I'm only showing positive part of the residual image, just to avoid confusion. So given this initial rendering, primary school arithmetic reformulates the problem of rendering the new image as a control variant, the old image, plus some residual. So this is the same multi-level Monte Carlo framework as used by Fabrice Roussel and colleagues in 2016. So expanding out this residual, it's the difference of radiance contributions of the paths in each frame. So yeah, the difference between the two frames. But we want to write them under the same integral so that we can simulate just this difference radiance, and this can be achieved with this reformulation under the common space can be achieved with a change of variable, which we call a path mapping. And we'll discuss this mapping later. Bundling up all the terms in this integrand together, we can think of this problem as simulating some sort of a difference radiance quantity. And the final equation is integrating the difference contributions over all paths. There won't be too much math, I promise. So back to the motivation. So we assume that there are only small changes in the scene between the two frames. And in such cases, most paths in this residual will not be affected by the movement, so they will have zero radiance contributions. So let's not waste resources recomputing those unaffected paths and focus on the affected ones. So then we need to characterize these affected paths. And here's an example. From the left frame to the right, the new frame, the green triangle is moving to the right. And we call it a dynamic object. Meanwhile, we imagine there's this corresponding ghost object in the new frame to mark the position of that object in the old frame. So yeah, as we said, some paths don't interact with the moving object at all, and we call these static paths. But here's this red path which bounces off the dynamic object, and that path doesn't exist in the previous frame on the dimmed image on the left, because there's no object at that point to bounce off of. So we called it this dynamic path. And another such path is this blue one, which goes through the imaginary ghost object in the new frame. But again, this path does not exist in the previous frame because it will be blocked by the object. So if we hypothetically isolate all static and dynamic paths in separate spaces, our goal now is to compute only the dynamic paths, since these are the only ones that are guaranteed to have non-zero radiance difference contribution. So we need a way to find these dynamic paths efficiently. And our intuition is simple. So we want to make sure that all the paths that we sample interact with the dynamic or ghost objects. And to guarantee that, we can start sampling those paths from those objects, basically from the middle of the scene rather than, as done traditionally, from camera or light sources. And we propose a bunch of techniques in the paper, and plus some defensive classical path tracing here illustrated on the very right that rejects static paths. But the core are two the most generic techniques, and I'll show how this works. And the other four are variations. So first technique, again, right? We're starting sampling the paths from the middle of the scene, from these objects. The first one starts from a dynamic object, the solid shaded here. So we take a point on this object, sampled through area sampling. Then we pick some direction using cosine hemisphere sampling, and we take this direction to go towards the sensor. Given that direction, we sample another direction using VRDF sampling, and we take this one to go towards the light. And now we start doing classical path tracing, where we trace paths along, we first trace the rays along these projections, connect to emitter and sensor, just like in next event estimation. And we also extend paths, both subpaths, randomly, and extending connections at every vertex that we sample. And we have derivations of PDF computations in the paper. So the second technique is very similar, only that it starts from this ghost object. Again, a vertex first on its surface, but then now we sample uniformly a direction, so we want this path essentially to go through the object. And this direction extended in the opposite directions give us essentially a dynamic edge that passes through this point. And again, once we hit surfaces from both sides, we extend directions and do connections as before. And again, PDF computations in the paper. Right, so our techniques cover all the dynamic paths, though one such path can be produced by multiple techniques. And here we have an example where this path intersects the dynamic object once and the ghost object 4 times. And so it can be sampled by 5 different techniques, essentially taking either of those 5 vertices as the starting point. And surprise, surprise, we use MIS to combine these techniques in a good and an unbiased way. Here's an example where first I show the raw difference contributions of each of these techniques. Again, here the box in the corner is moving to the right. So these are raw contributions from each techniques. And at the bottom, after MIS weighting, and when we sum them up, these images on the bottom row, we get our difference image. Again, showing positive differences here, only just to avoid confusion. There are negative differences with comparable magnitude. So there's one more thing to mention before revealing results. Recall our goal was to compute this residual image, and we formulated it as a path interval over a common domain, but we still need a mapping once we sample a path in the new frame, we need a path, corresponding path, TP, in the old frame to evaluate this difference contribution, right? F2 and F1 are 2 different radiance contributions functions, and P is what we sample, and T of P is this mapping that transforms this path from the space of the new frame to the space of the old frame. Luckily for you, I'm not going to go into details, but the gist of it is that the goal of designing a good mapping is to increase the correlation between paths in the 2 frames. So once we sample a path in the new frame, we want to map it to the old frame, but with minimal changes, so that we have a low variation in this in the difference between the two. So these are called shift mappings in gradient domain rendering, and Rister GI works. I don't expect you to be able to read all these references, but believe me, there is prior work on this. We call these path mappings, not shift mappings, because just to avoid confusion, that we're not shifting pixels as is done in those prior works. So yeah, but just to convey the effect of a good path mapping, here is a reference residual image rendered with many samples in a standard technique. Again, showing positive differences only for clarity. And here's the same image rendered using our techniques, but without path mapping, which essentially means sampling in the two frames separately and subtracting the results. Essentially, this leads to paths that are not very well correlated, so there's variance in this difference computation, which you can see here is manifests as noise in this image. And with this path mapping, we can reduce the variance by a good amount. So slowly moving towards results. So first we focus on rigid motion between frames, but material editing is a actually simpler special case in this framework, where essentially there is no motion and there's no ghost object. And the path mapping conveniently is just an identity. And our baselines are classical path tracing, where essentially we render this new second frame from scratch, as you would traditionally do. And the second baseline is rendering just the residual image, but using correlated path tracing. So essentially, we trace one path in the new frame, one path in the old frame, using the same random sequence, which this correlation provides. Yeah, so this kind of correlated sampling produces reasonably correlated paths for path tracing, and it's actually how some related works from gradient domain and Rister works actually do it too. Here's our classic Sponza scene, but there's a ninja throwing 3 shurikens from the old to the new frame. Here's the new scene rendered using path tracing from scratch. And even on my screen, I cannot see the differences, but I will show zoomings in a second. On the top is the residual image in false color, now showing positive and negative differences in different colors. Blue parts are negative, not that you really care, but... and here is our incremental rendering, and there is difference. Let's hope we can see it now. Right. Cool, there's a reference on the right, path tracing from scratch. This is the second frame, right? So we're only showing the second frame, and now we're just applying standard path tracing from it. It's all like the same time budget in this comparison, so we call time rendering. This one is noisy. Correlated path tracing is less noisy in the static parts, but actually more noisy in the dynamic parts. And this is rendered using our framework with our techniques and our mapping, showing reduced noise overall. There is some ghosting. We'll come back to this in a bit. Another example, this is some dining room scene, and what's moving? The hook there is moving. Let's say, so it's moved, it's moved somewhere, on the table. Again, this is path tracing from scratch. Hopefully, you can see some more noise, more obvious here. This is the residual image. The differences, there's actually quite a bit of differences here due to global illumination effect. And this is our incremental sampling showing nice reduced noise. Not showing correlated path tracing here for some reason, I'll ask. But there's another example. Here we're editing material. So here we have a light source shining at a book. The book has a blue cover. So now we change the material of this cover of the book from blue to white. This is how the standard path tracing will perform. Again, right, this is just rendering this new frame from scratch. This is using our approach with the same amount of time, much less noisy. Now you can imagine, yeah, when the scene is changing from blue to white, right, the difference will be yellow. And these are residual images now, computed using the correlated path tracing. So the better technique for computing, the better baseline essentially, and our residual, again, much less noisy. Overall, we achieve speedups of ranging between 2 and 5 times for motion, and for material editing 4 to 16 times in terms of variance compared to correlated path tracing, and oftentimes orders of magnitude compared to traditional re-rendering of the new frame from scratch. Right, so sometimes we observe ghosting at the position of the object in the old frame. Okay. This is due to inconsistent, essentially, noise level compared to where the object used to be versus static pixels. This is just an inherent limitation to the image space control variate method, but it is unbiased and does converge with more samples. Now, developing denoisers tailored to such residual noise can be an interesting future work, and interestingly, a differentiable rendering could benefit too from such techniques, because you may have guessed there's a strong connection between our method and differentiable rendering. This is simply because our finite difference image is essentially can be thought of as an integral over motion derivatives along time. So here is an example where 2 triangles move from one frame to the next, and this is I'm showing the difference images. The left one computed by integrating different derivative images over time, and the right one is simply subtracting frame 1 from frame 2. Right. So here we've used edge sampling to compute these derivative images, and then we simply integrate. Okay, nearly done. Some limitations. First, right, no sampling technique is perfect in all cases. We employ path tracing as an extra technique to incorporate some advantage of camera tracing, for example, when we see when the moving object is very close to the camera. Better adaptive sampling can be used in future work. We also do not target dynamic or camera lights, because in that case, all paths are essentially affected, so it may be more efficient to render the new frame from scratch. And similarly, where there's a lot of movement in the scene, right? If the whole scene changes, then this residual has a lot of energy comparable to the energy of the frame itself. So you might as well just re-render. And as we saw a couple of slides back, sometimes there's this ghost noise. The variance essentially is concentrated at the positions of the dynamic and ghost objects in the image. And our eyes are obviously sensitive to inconsistent noise levels across the image. And also glossy objects seen from the camera, they can be noisy, as in classical light tracing, because our techniques start from the middle of the scene and connect to the camera. The forward tracing that we employ as a defensive techniques helps, but we need to use it sparingly because to avoid its overhead of its otherwise blind sampling. So to sum up, we have a residual path integral framework. We show some initial practical applications to scene re-rendering with rigid motion and material editing, but the algorithms are far from being exhaustively explored or optimized, so we hope to bring more attention to the re-rendering problem. And that was it from me. Cheers.